So the next conic section we'll take a look at is the hyperbola, and it is related to that ellipse in many ways in terms of the terminology and all the process to graphing it as well, although they're very different graphs. Obviously this one here kind of looking like it's almost like a parabola. It does not have the same exact shape as the parabolas we've seen, but just a kind of U-shaped curvature. But again, this is one graph. Also notice this is not a function in the sense that it doesn't pass a vertical line test. But the idea that these are all part of one graph that describes one equation. So with graphs of hyperbolas, what we want to understand about them is there's two types. There are kinds that you could say open left and right, and kinds that open up and down. And so we usually refer to these as the horizontal hyperbola that opens left to right, and the vertical hyperbola, the one that opens up and down. Now, there's a term that we use for the axis that runs kind of through the graph. And it's actually a little more clearly labeled up here. Of the two axes, as in up and down, left and right, x and y, the x-axis here, in this case, the one that runs through, as in hits the graph itself there and there, is being referred to as the transverse axis. So much like the parabolas, there is a center, but now the labeling of this axis as a transverse axis is not necessarily concerned about which axis is larger or longer or bigger, like we would refer to the major and the minor axis for the ellipse, but rather just the axis that hits the graph. Notice the other axis will not. The other axis will go between the two pieces of this graph. But the axis that hits them we refer to as a transverse axis. That will have the center there. It will also have these points, which we will refer to as the vertices, right? Vertex, the two different vertex of vertices. Notice we again have the word focus, and we have foci. And in this case, you can think of these points as the points that the graph is kind of wrapping around on each side. You'll notice that in each case. It's the point that is between the center, the graph is between the center and this foci is where the vertex falls, and it kind of wraps around that point and wraps around that point. So that's one way to kind of visually think of the foci for these hyperbola. Now, as far as the formulas are concerned, you'll notice that there are now two forms, and that's important because for hyperbola, to get this graph versus this graph, notice the difference. The only difference comparing this formula or this equation to our ellipse equation is that it's a minus instead of a plus. That's the only difference. X squared quantity, y squared quantity equals 1, but a minus instead of a plus, drastically changing our shape. But with a minus sign, we want to understand that this here with x squared quantity minus y squared quantity is a different function, a different equation than y squared quantity minus the x squared quantity. And it turns out that this is the difference that makes. The order, or you can think of it which one comes first or which one's being subtracted, whichever way, that makes the difference. So the way I like to think of it is if the x term is first, right? That's the positive fraction, not the minus, the negative one. If the x squared comes first, for x, think horizontal, right? The x-axis measures horizontally. So for the x coming first, that is your horizontal hyperbola. That's mentioned right here. If the y term is the one that comes first, then that is going to be your vertically, your opening up and down hyperbola. Okay? Also, we still have A and B. They're going to function a little differently. Obviously, this is not an ellipse that we're just stretching, but some aspect to the direction of x and y will relate to those A's and B's. And then we do have C as well for the foci. It's a different foci formula, though. If you recall, the last one was a squared minus b squared. This one we're getting c squared is a squared plus b squared. So the actual, looks like the Pythagorean theorem. But let's look at how A and B really are related, because you'll notice now A will always be related to whatever came first. That's how we're going to define A. A squared is that denominator under whichever term was first, whether it was x or y. Again, for ellipses, A was always with the bigger one, whether it was the under the x or under the y, whichever one was bigger was the one we called the a squared term. Now it's whichever one is first will be associated with the a squared denominator. Okay? So with that, now we want to take a look at this role of A and B, and what I've done is I've given you kind of like the formula version of how to create what are these asymptotes. Because as you see these two graphs here, like I said, they do not behave like a parabola. They are actually asymptoting at two different slant asymptotes, I should say, diagonal asymptotes. So these two lines that you see drawn in these dashed lines, from this point, from the vertex, our graph is actually going to get closer and closer to that line, but again, never cross it. And it's going to asymptote in that behavior in all four directions there. So these asymptotes are very important to the creation, the sketch of our graphs of our hyperbolas. Now you can use these equations of the graphs of the lines, but I think it's much simpler to just recall that when you go to create this, and we'll see this as we graph several on the next pages, like we said, A will be associated with the first term, so whether that's your x term or your y term is important. B will be associated with your second term. But in this case, if A is associated with x, go from your center out the distance A in each direction. Then B associated with y, go the distance B in the y direction, and create this thing that we call the central rectangle, or I sometimes call it the inner rectangle. The central rectangle will be that distance of A in each direction, B in each direction, and the rectangle that would connect those locations. Then use that rectangle and connect the corners to create your asymptote lines. That's it. Rather than trying to remember B's over A's and A's over B's, I think it's visually much simpler to just measure distance A, measure distance B, again, associated correctly, and then draw your rectangle and connect the corners. And same thing with the vertical hyperbola, same exact idea, only now obviously A is associated with Y, B with X. Create the rectangle, connect the corners. Okay, so we'll see that on these next several pages, next examples. Again, with the foci, we want to remember the c squared equals a squared plus b squared formula. Also, here's the two different descriptions for what happens when we shift it off of center. What's very important here, though, we've kept a under the first term and b under the second, right? But what we do want to kind of understand is the x and the y and their relationship to h and k to find your center. Make sure you realize h always pairs with x, k always pairs with y to give you h comma k. So when you run into the situation of a vertical hyperbola where your y term comes first, understand that's got to be your k there and your h there for your h comma k center. It's still got to be h gives you x, k gives you y. That's the very important idea to keep straight there. Other than that, it's the same idea of shifting the center and then using a and b always based on the center. So let's take a look at a couple examples where there is no shift. Notice there's no adding or subtracting to the x's and y's here. I'm going to go ahead and also, besides finding the vertices and foci, I'm going to just label that with this one, with x squared coming first, we would call that a horizontal hyperbola. So just understanding that means that will open left and right if we were to graph it. But then the a and the b, right, we're always thinking of a there and b there. So a equals 4 and b equals 3. So it says find the vertices and the foci. Well, let's go ahead and talk about where the vertices would be. Since this is a horizontal hyperbola, and even just to draw a quick sketch, horizontal meaning opening, curving, the lefts and the rights. The center is here, so we need the a, we need, I should say, the x direction, which in this case will be the a, to get from our center out to those 2 points, right? We have to go left and right to get to the vertices. So that a tells us how far left and right to go from our center, which again was 0, 0, to get to those vertices. So the vertices would be plus and minus 4 to the x coordinate. So 4 comma 0 and negative 4 comma 0. Okay? Now, remember the foci are supposed to be the things these graphs curve around, so they should be further, but again, on this what we call transverse axis, right? The one that crosses through the graph. So again, on the x direction, now in this case, we need to use our foci formula to figure out that value for c. So c squared equals 4 squared plus 3 squared, or 16 plus 9, so 25. So c is going to equal 5, right? Since c squared equals 25. So c is 5. And that 5, again, will be the distance left and right of center. So our foci will be at 5, 0, and negative 5, 0. I really think even just drawing a basic sketch like this is very useful to help you understand, once you find C, what it affects, where it, where that value is added and subtracted to find those foci. So there's the foci and the vertice. Looking at the next one, we've got the y term first. So this is a vertical hyperbola. Okay. Still, the a and the b is how we consider them labeled. So a is 3 and b is 4. So now, again, centered at 0, 0 still, but with a vertical hyperbola, we expect that kind of behavior. So now 0, 0 there. To find these vertices, we're up and down, right? Which for the y will be the a value of 3. So for our vertices, from the center, we want plus 3 and minus 3 to the y value. So 0, 3, and 0, negative 3. Again, just notice the difference. Here, we added a to the x's. Here, we add a to the y's to get to those vertices. Now we'll use our foci formula, which, since a and b are the same, just reverse. This is going to look identical, just 3 squared plus 4 squared. So 9 plus 16, so 25. So again, we get c as 5. And now, with the c of 5, notice the foci would be above and below the center for them to wrap around. So again, the c has to get added and subtracted to the y value of the center. So the foci are going to be at 0, 5, and 0, negative 5. All right, and now let's look at the simplest form of an equation and graphing it. So essentially what we just were doing, only in addition, finding the graph. So for this one, we've got that's going to be our a squared and our b squared. Again, without anything affecting the x and the y, we have a center at 0, 0. Let's just plot that, 0, 0. So a is affecting the x, b is affecting the y. So let's use that a and b. A is 5, b is 4. Let's take from our center and go out 5 in the x direction and 4 in the y direction. And while we're at it, let's create that thing called the central rectangle. So I didn't really put points there. I put those little dashes to show where my rectangle will go. Now, what I want for points is the question of what kind of hyperbola we've got here. So since the x came first, this is a horizontal hyperbola, opening left and right. That tells me that this and this are going to be the locations for my vertices. But before we draw anything, let's create those asymptotes by simply connecting the two corners. The corners through the center give us the lines for our asymptotes, and now it's a sketch of, from this point, asymptoting up and down. Same thing here, up and down, to get a good sketch of our graph. And so we can now label, we can identify the location of those vertices we just plotted. The vertices are at the 5, 0 and negative 5, 0. And we can use the a and the b in our foci formula to say 5 squared plus 4 squared, so 25 plus 16, so 41. So that means c is the square root of 41, which does not simplify nicely. So let's just get an approximate for that, so we know roughly where to put these. So about 6.4 roughly. So down here, if I were to go 6.4, I'll go ahead and put a little asterisk at plus and minus 6.4 as the location of our foci. But to find them exactly, we again say that this c has to get added and subtracted to the x coordinate from our center, right? Where that distance c to the left and to the right. So the foci are at root 41, comma 0, and negative root 41, comma 0. Right? That's that distance c to the left and to the right of our center, which was at 0, 0. So there's our foci, and there's our vertices.